This is part 2 of the lecture covering sound. This lecture is specific to Conceptual Physics AB. In this lecture, we begin to examine loudness. The word loudness is a physiological term. That is, it describes our senses. What is the physical quantity, however, that loudness corresponds to? That's a new quantity for us. It's called intensity. Okay, so loudness is a physiological term. It describes our senses. Specifically, of course, our sense of hearing. And it corresponds to a physical quantity called intensity. Okay, now intensity is a definition. The definition of intensity is that it's power divided by area. Okay, now recall from the unit on work and energy that power is energy divided by time. So it's measured in joules per second, which are referred to as watts. And then what we're doing is we're taking the watts and we're dividing it by area, which is in terms of meters squared. So the units then, therefore, of intensity are watts per meter squared. Okay, now there's two ways to think of it. You could talk about intensity in terms of the production of a sound, or you could also talk about it in terms of receiving the sound, for example, as you listen to the sound. Let me describe it first of all in terms of the production of a sound. So let's say, for example, that I consider my voice to be a point source of sound, and then as I speak, sound waves expand outwards from that point. Recall that sound waves are spherical longitudinal waves that are propagating through the air. As that energy, however, expands outward, it spreads out over an increasingly larger and larger surface area, the surface area of a sphere. The geometrical formula for the surface of a sphere is 4 pi r squared. So then therefore we can describe intensity of the sound associated with the production of sound in the following way. Okay, so let's say right here is a source of sound. And let's consider it to be a continuous source of sound. So then therefore it would be me doing something like this. Like so. It costs me a certain amount of energy per second in order to produce the sound. This is referred to as P source, the power output of the source. And then that energy expands outwards over an increasingly larger and larger surface area associated with a spherical sound wave. This spherical sound wave has a radius r associated with it. Okay, now, the intensity I then, when you're a distance r away from the source, would be equal to the power output of the source, that's in terms of watts, divided by the surface area of the sphere, 4 pi r squared. That's the geometrical formula for the surface area of a sphere. Notice that, like the force of gravity, intensity obeys an inverse square law. And the reason for it is because we live in a three-dimensional universe, specifically in this case, this three-dimensional sound wave, which has a surface area of 4 pi r squared. The way that an inverse square law works is as follows. If you are standing, for example, twice as far from the source, then the intensity is 1 over 2 squared, or 1/4 of the original value. If you're 3 times further away, it's 1 over 3 squared, or 1/9 of the original value, and so on. We could also, however, describe intensity in terms of receiving the sound as well. So let's say, for example, that we have an observer that is standing here listening to the sound. When you listen to the sound, that energy per second is passing through what is called a cross-sectional area, specifically the cross-sectional area of your eardrum. Think of your eardrum as like a little box, like so, and the area of that box is A. So then therefore we could talk about the intensity of the same sound, it's the same sound wave. We could talk about the intensity of the sound in terms of the amount of energy that you receive per second per area of your eardrum. So we write the intensity I in terms of what is called P receive. That's the amount of energy that you receive per second as it passes through the area A of your eardrum. So there's two ways to think of intensity. You can talk about it in terms of the production of sound or in terms of the reception of sound, okay? Okay, let me do a little bit of erasing here. Okay, now let me describe intensity in the context of what we perceive as loudness. The softest audible sound, the intensity associated with it, is next to nothing. It's 1/1,000,000th of a watt per meter squared. This quantity is referred to as I0. I0 is equal to 1 times 10 to the minus 10 watts per meter squared. That's 1/1,000,000th of a watt per meter squared. It's next to nothing. So what does I0 sound like? Well, I0, for example, sounds like this. If you could still hear my voice as we recorded this video, you are hearing an intensity of about 1 times 10 to the minus 12 watts per meter squared. Okay, now if you could barely hear me speaking through the recording of this lecture, then you were probably hearing an intensity that was pretty close to I0, 1 times 10 to the minus 12 watts per meter squared. Normally I demonstrate this by standing next to a student here somewhere in my classroom, and then I speak in a very low whisper. Okay, now what we perceive to be a doubling in loudness corresponds to an increase in intensity by a factor of 10. What we perceive to be a doubling in loudness corresponds to an increase in intensity by a factor of 10. So for example, consider the intensity be to 1 times 10 to the minus 11 watts per meter squared, which is 10 times as intense as I0. We then perceive this to be twice as loud as this. Okay, consider an intensity of 1 times 10 to the minus 10 watts per meter squared. This intensity is 10 times this amount, so this sound we perceive to be twice as loud as this. This intensity here, however, is 100 times greater than this intensity here. However, we would then perceive this sound to be 4 times as loud as this, and so on and so on. Because of this fact, that is, how we perceive a doubling in loudness corresponds to an increase in intensity by a factor of 10, we define a logarithmic scale to describe loudness. This is referred to as the decibel scale. It's also sometimes referred to as the intensity level. Now, I know, of course, in conceptual physics, you may not have advanced in mathematics class far enough to be familiar with logarithms. So I'm not going to go through the actual scale itself here in class for that reason, but let me give you a basic understanding as to how the scale works. So this is sometimes referred to as intensity level. And this is what is called decibel scale. Decibels is abbreviated as dB. Okay, the scale itself is defined in terms of I0, the softest audible sound. By definition, I0 is 0 decibels. And then if we have a sound that is 10 times as intense as this value, and is then therefore twice as loud, this corresponds to an increase in the intensity level by 10 decibels. So in other words, the intensity level of this sound is 10 decibels. This sound here is 10 times as intense as this value. That corresponds to 20 decibels. So 20 decibels is twice as loud as 10 decibels. 10 decibels is twice as loud as 0 decibels. This means that 20 decibels is 4 times as loud as 0 decibels, and so on and so on. That's the basic idea as to how the intensity level or decibel scale works. What we perceive to be a doubling in loudness corresponds to an increase in intensity by a factor of 10. That corresponds to an increase in intensity level by 10 decibels. The Richter scale, by the way, which describes the intensity of seismic waves, works much the same way. So, for example, compare a Richter scale 5 and a Richter scale 6. A Richter scale 6 is 10 times as intense as a Richter scale 5. A Richter scale 7 is 10 times as intense as a 6. It's 100 times as intense as a 5. It's another base 10 logarithmic scale, very similar to the decibel scale. Okay, a couple of other levels of intensity that I want to briefly describe. Okay, first of all, when does sound become painful? Where you could actually, for example, damage your hearing while listening to it, say while you're standing, for example, in a concert hall and the concert is indoors. If you've ever been in a concert, for example, and you've stood right next to the speaker or right next to the PA, you may have noticed afterwards that your hearing for a day or so, for at least a few hours, sounded kind of muffled. Or you hear like a really high-pitched whine in your ear after the concert. Well, if you've done that, or if you've experienced this, you have suffered a little bit of hearing damage. You are suffering from what is called tinnitus. It's also pronounced tinnitus. At any rate, however, your body, of course, has the ability to heal itself. It's like scabbing your knee, for example. Eventually, of course, your hearing will return after just a couple of hours. Your body heals. However, if you do repeatedly expose yourself to really loud sounds, then you can actually permanently damage your hearing. The easiest way to prevent this, of course, when you say go to an indoor concert and it's really loud, is just wear earplugs. Don't take the earplugs and stuff them all the way into your ears. Instead, kind of place them loosely in your ear canal, and that will then absorb enough energy to lower the intensity level below what is called the threshold of pain. The threshold of pain, when sound actually becomes painful, is an intensity of 1 watt per meter squared. It's 1 trillion times as intense as I naught. On the decibel scale, it corresponds to 120 decibels. So if you're standing right next to a speaker in an indoor concert, you're getting 120 decibels. Once again, the easiest way to protect yourself is to use earplugs, or quite frankly, even easier than that, take advantage of the inverse square law. Just move further back from the speaker, and then therefore the intensity will be below this value, and the intensity level will be below this value here. What about louder sounds still? Well, if you're talking about sounds that are louder than the threshold of pain, you could literally get to a point where the amplitude of that pressure wave is so large that it actually could blow your body apart, as strange as that sounds. That's referred to as the threshold of death. At the threshold of death, the intensity of the sound is 1 million watts per meter squared. And the intensity associated with a pressure wave this large, well, it's literally large enough to disrupt your body and then therefore kill you. That's a value of the intensity level, by the way, of 180 decibels. At that point, it really doesn't make any sense to talk about it in the context of sound. It's just an extremely large pressure wave that is propagating through the atmosphere. Okay, I'm going to end this video here. In the next portion of the lecture, we'll do some example problems where we'll see how intensity relates to what is called the inverse square law.